So you've seen how to find the volume and area of cylinders and prisms from the other videos. This video is going to explain about the volumes of kind of special case or weird cylinders and prisms. So what you should know at this point is if you know the distance around your cylinder or prism, then you should be able to find, if you take that distance and go all the way down and all the way up with it, if it's the same all the way, then you should be able to find from the circumference, you should be able to find the lateral surface area. It's the circumference times the height. Or if it's a prism, it'd be the perimeter times the height. So that's this lateral surface area. The circumference times the height. The circumference is 2 pi r times the height. And you should be able to find the total surface area too. The total surface area, you're going to take the area of this base and on down the area of the bottom base, and you're going to add those two to the area of the sides, the lateral area. So that's what the total surface area is, the lateral surface area plus 2 bases. Of course, the lateral surface area we said was the circumference times the height, and each circle on the top and bottom in this case is pi r squared, so you have 2 of those pi r squared, so that's a total surface area. And you can also should be able to find the volume at this point. The volume, if you take the area of the base times the height, then that should give you the total volume. The area of the base times the height, because this is a circular prism or a cylinder, the area of the base is pi r squared, so you get pi r squared times h right there. However, what if the base is not a circle, triangle, or square? What if you have to find, say, the area of this times the height, the area of a pentagon times the height? Well, let me try to show you on a hexagonal prism. So here I've got a pot, and the top and bottom are both 6-sided. They're regular hexagons. Remember, they're regular because all of the lengths are the same and all of the angles in here are the same. So all the lengths are the same, all the angles are the same. That makes it a regular hexagon. There's 6 sides, so there's 6 sides to this prism on the lateral surfaces. And to find the area of this, of course, the reason we're doing this is because once we find the area of the top, we can multiply that times the height of the prism and get the volume of the prism. So to find the area, we're going to take the hexagon and break it into triangles like this. And you can see there's 2 right triangles per side. And when we want to use right triangles, triangles are so simple, it's easy to find the area of a triangle. It would be 1/2 base times height. So maybe if I put it like this, you could see the base and the height. And then the right triangles, of course, we have SOHCAHTOA and Pythagorean theorem that we can use to figure out things about them. So if we know the length of a side of this hexagon, this side of the triangle is 1/2 the length of the side. So that's pretty easy to figure out. Also, if we look at, we can figure out this angle here in the triangle because it is part of this circle. And if we know how many triangles there are, let me show you another picture I already drew. Here, you can see there's 2 triangles per side. So with 6 sides, there's 12 triangles total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 per side. That means we take this circle, and there's 12 of these angles in it. So 360 degrees divided by 12 means this angle is 30 degrees. Now that we know this angle and this side, we can use SOHCAHTOA to figure out this side, the distance from the center out to the side. That's actually called the apothem of this regular hexagon. Of course, again, we know this side is half the side of the hexagon. We know this angle is 1/12 of a circle, and we know this side because we can use SOHCAHTOA. This angle, this side, and this side would be the tangent of that angle. So once we figure all that out, we got the area of this side, 1/2 1/2 S times A. And once we know that area, times 12 gives us the whole area. And now we can use that area times the height to find the volume of the pot. So let me just summarize again what was going on with that hexagonal pot. Here I have, this one's a pentagonal prism, so the top is a pentagon, and the prism has 5 sides. The bottom is another pentagon. The cross section taken parallel to a base anywhere here is going to be that same pentagon. And here's that pentagon. Remember, the way you do it now is you figure out how many triangles are you going to have? There's 2 per side. To figure out what this angle is up in the center here, you would take this circle and divide it by however many triangles you've got. So the angle measurement is 360 divided by 2n. This length, again, that's called the apothem. And the apothem, you're going to have to use SOHCAHTOA to figure it out. So the tangent of the angle is the opposite over the apothem. The opposite down here is, again, half of the length of the side. So if you know the angle on the side, you can figure out the adjacent side, which is the apothem here, using this formula, SOHCAHTOA. After you know what the apothem is, and you know what this side of the triangle is, well, the area of the triangle is 1/2 base times height. 1/2, a half S times A. And then you'll have however many of those triangles you've got, gives you the whole area. In this case, it was a pentagon, so you'd have 10 of those triangles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the hexagon I did the example of, you would have had 12 of those triangles times the area of a triangle. So that's how you can find the volume of a prism where the base is not a circle for a cylinder or a triangle or a square, or something easy to find the area of. The second example I had for you, remember going back to my introduction, was oblique solids. So talking about oblique solids, again, you know how to find the surface area and volume of this, but what if this is at an angle? Let me explain. Well, actually, hang on a minute. I've got to go do something real quick. So over here by my front door, what I was going to do, I got to count my money. I have a casserole dish over here, and every time I come in the front door, I throw my pocket change in there. So I'll just take a break from the lesson so I can count my pocket change. Actually, this is part of the lesson. You'll see in a minute. I have a point to make. Okay, I've got all my change sorted out and stacked up, and you can see most of the stacks, including these 3 here, are perpendicular to the table. They're going a right angle to the table, straight out of the table, and that makes them cylinders, right? The top is a circle, the bottom is a circle, both bases, and every cross section, if I was to cut cross sections this way, horizontal cross sections, every one of them would be a circle, right? That's a circle there. If I were to cut it down lower, that's a circle there. So every cross section is a circle, both bases are circles. This is a cylinder of coins. And if I counted the number of coins in there, I could figure out how much money there was. Now, these two are the same, but these two, they come straight out of the table at a different angle. This one's coming straight out at, it's not a right angle. Something that's not a right angle is called an oblique angle. So that's an oblique angle. This one would be an oblique cylinder. This one, it's all jig-jag, it's not coming straight out, but it's still, every cross-section would be a circle. So just because these are at a weird oblique angle and a weird zigzag design, does that mean they have a different amount of coins in them? They're the same exact height. No, clearly there's the same number of coins in them. So the volume is the same regardless of the angle. Not true with surface area though. Let me show you that. So look at this square prism. It has a square on the bottom. The square has a length S, and S is the length of the other side. All the lengths are S. The top is the same square. If you cut a cross section anywhere through it, let's move this cross section up and down. The cross section would also be that same square all the way up and all the way down. So you can see that. And the height of a side of this is the same as the height of the prism. So there's the height of a side, and it's the same as the height of the prism. You can see that. So the area of the side is going to be the height of the prism times the length of the side, h times s. Simple enough. But what if the prism is oblique? So here's an oblique prism. It has the same height as the right prism. You can see here the angles are not at a right angle to the base. So this one's off at a slant. And here you can see h is different than L. The size of this rectangle is not the same as the size of that rectangle. The surface area of this lateral side here, is different than this lateral side. However, if we put a cross section in there, it's that same square all the way up and all the way back down. That same square. It has the same volume. It's even more extreme in this other example over here. If you really tilt it so this angle's a pretty oblique angle now. These are both oblique prisms. Remember that word oblique. Then if we do a cross section here, you can see the cross section is the same all the way up and all the way down. It's that same square. But the slant height, this length L, the height of a side, is very different than the height of the prism itself. This height is the same as this height is the same as this height. All three prisms are the same height. But because this one's on such a slant, that length is much larger and this side is going to be much larger, which means the total surface area is going to be much larger than the area of this one. But the volume remains the same. That idea is called Cavalier's principle. So for an oblique cylinder again, the circumference is the same, just like a right cylinder. The circumference is the same all the way down, just like it is for a right cylinder. It's the same all the way down. So if you take a cross section perpendicular to the base, it'll be the same shape as the base. Because the same circles here, it's going to be the same area all the way up and down too. So right over here, this one, the oblique cylinder, is going to have the same area. No matter where the cross section is, if you look in the middle, it's going to be the same as the top. If you look at the bottom, it's the same as the top, right? Bottom base and the top base, and everywhere in between has the same cross-sectional area. And so for this, the circumference and the base area are the same as it would be for this one. If you want to look at surface area, again, surface area is hard because you'd have to get into some serious trigonometry to figure out what that angle is and how does it affect the lateral surface area. So the lateral surface area is tricky, and because of that, we're not going to cover that this year. But the idea for the total surface area is still going to be the same. The lateral surface area plus this base plus the other base is the same idea. But again, we won't be able to calculate that based on this year's lecturing. The volume is the exact same as it was before. That's the whole point of this. It doesn't matter if it's at a right angle or at an oblique angle. Cavalier's principle says the volumes are the same.